All right. So welcome back, everybody, to this session of the Cardiff Analysis Seminar. Today, we're delighted to have Shipman from Louisiana State University, who will talk about embedded eigenvalues of the Neumann-Poincaré operator. So the floor is yours.
Okay. Thank you, Mike. And thanks for coming so early in the morning, 7 o'clock. Yeah, so I've been interested quite a bit in embedded eigenvalues of different types of operators, integral operators and differential operators, and why they occur and their applications. And so this particular talk is a presentation of work that I've been doing with Wei Li at DePaul University and Karl-Mikael Perfekt at University of Reading. And what we do here is we construct embedded eigenvalues for a boundary integral operator known as the Neumann-Poincaré operator coming from potential theory. And I want to show you, so today I'm going to show you basically the theorems and try to show you how they work. Okay, there's a lot of technicalities that I'll have to skip, but I just want to show you how they work, and I'm not going to do too much about applications either. So this is really integral operator and how you can get embedded eigenvalues. First I'll introduce the Neumann-Poincaré operator from potential theory. It's a boundary integral operator that arises in electrostatics and basically scattering in quasi-static regimes. And it's a situation where you have electromagnetics in, say, electrostatics, so you have a potential, and you can reduce the problem to a problem on the boundary, this boundary integral equation. And the operator involved there is the Neumann-Poincaré operator. And it turns out that eigenvalues of that operator are related to what people like to call plasmonic resonances. And those words have been thrown around a lot, but basically the spectrum of the Neumann-Poincaré operator is related to fields, electrostatic fields that exist in the absence of a source. And what's interesting is that so what allows us to construct embedded eigenvalues is two things. One is that you need a domain with corners or conical singularities. And so corners in 2D, conical singularities in 3D. The reason for that is that without the corners or conical singularities, you won't have the continuous, or you won't have the essential spectrum. And the other ingredient is that you have a certain symmetry, that the domain, the domain where the Neumann-Poincaré operator is occurring on the boundary of that domain needs certain symmetries, and those symmetries allow you to decompose the operator into the different components, and in that way you can find eigenvalues that are not embedded for one of the components that end up being embedded in the continuous spectrum for the other. So those are the two ingredients: corners, singularities, and symmetry. It turns out, so in some of my work in differential operators and in quantum graphs and so on, that I'm particularly interested in how to obtain embedded eigenvalues in the absence of symmetry. In other words, eigenvalues that are not induced, or sometimes people say protected by symmetries. And I don't know how to do that yet for the Neumann-Poincaré operator, and I don't know if it's possible, but you might say that using symmetries is kind of the easy way to do it. But it turns out that the analysis here for NP operator is quite technical, and was not easy, at least not for us. Unless Kala found it easy. I don't think any of us actually did. So let's see. So let me just talk about some of the history the Neumann-Poincaré operator with respect to its spectrum, particularly. There's some works, there are lots and lots of works on the Neumann-Poincaré operator. But starting in 2 dimensions, so imagine that you have just a domain in 2D, and it could have a corner, like right here, some kind of domain. And Karl-Mikael back in 1916 wrote a dissertation, a long dissertation, which is brilliant. And it's interesting how, even without it's the Fredholm theory that was really coming about, the Fredholm theory for integral operators that was coming about at that time. And he made huge strides there in that dissertation, in understanding things that we now understand in the context of functional analysis and the sublevels spaces. It was not routine at that time. It was not really even well established, but it's amazing how well he understood what was going on. And he claims through huge calculations to have proved that the spectrum for a 2D domain with a corner actually is continuous. And he writes down these integral superpositions of extended states to show the continuity of the spectrum. Now recently, I think it was published in 2019, maybe 2020, Karl-Mikael Perfekt showed that genuinely, yes, the essential spectrum really is absolutely continuous. You can find that the Reda-Nikodym derivative, the density of states. I didn't write that down here. Yes, I did. Here, the essential spectrum is actually absolutely continuous. So it took 103 years to do it, what we would, in a way that we would call rigorous. Maitreya in 2002 dealt with the essential spectrum in L2. So this is an important point and a theme here, that the Neumann-Poincaré operator, I'll define it. Actually, I didn't define it for you yet. Sorry, it's this operator with the kernel that's a derivative of the green function for the Laplace equation. Okay, I'm sorry, maybe I should have said that earlier. But so depending on the space in which that operator is acting, it can act in L2 or it can act in a space that's larger than L2, that's actually h minus 1/2. The essential spectrum is different because, I'll show you some pictures of what Maitreya did, where the essential spectrum is actually a certain region in the complex plane. But as soon as you go to what we call an energy space, the essential spectrum ends up being a self-adjoint operator. And there's a paper of Helsing, Kang, and Lim where there's numerical evidence. At least it was numerical evidence. It was interpreted as showing the existence of embedded eigenvalues, where you had a genuine eigenvalue inside of that essential spectrum. And then the results I'm going to show you today are proofs, or at least the results and some of the proofs of how you can actually create these embedded eigenvalues. And Wei Li and I were actually inspired partly by one of these numerical examples. Now in 3 dimensions, things do become quite a bit more difficult. And I'm going to show you our results also with Karl-Mikael Perfekt in 3 dimensions. And I'm going to mostly concentrate on that because that's the more difficult one, I think. And so in 2018, Perfekt showed, he analyzes the spectrum on L2, and in H star is that energy space that I talked about, where the operator becomes self-adjoint. And he analyzed conical singularities and also wedge singularities. We're going to do with conical singularities, try to use a symmetry with the conical singularity to obtain embedded eigenvalues. So here are the 2 theorems. The first theorem, 2019 theorem of Wei Li and me, concerns domains of this kind that you see down here. The only thing that's needed, the only essential properties of this region here are that it is symmetric about a line in 2D, and that it has also an angular discontinuity. I mean, not, it has discontinuity in the derivative, right? So it's Lipschitz, but it has this corner right here of some angle. And the theorem says that if the curve itself is C2 with reflectional symmetry, so some original curve that might be a blue one that's continued continuously or smoothly across this line, let that be gamma naught. And if it has reflectional symmetry and it's not a circle, then there exists a corner perturbation. This black part here, that's a corner perturbation of some size, such that the Neumann-Poincaré operator in the energy space that I will introduce actually has an arbitrary number of eigenvalues within a central spectrum. Now I realize that this is written in a way that we really would not accept for our students writing mathematics. It doesn't have an arbitrary number of eigenvalues. What it really means is given any number, there exists a corner perturbation such that you have that number of eigenvalues within its central spectrum. Actually, I'm pretty sure that I corrected that, but I don't know why it's not corrected in this copy. Interesting. Huh. Oh well, so there are going to be some typos coming up. And this is the recent theorem of Wei Li, Karl-Mikael Perfekt, and me, 2020. Oh, this one here, the 2019 one, is published in the Journal of Integral Equations and Applications. And this one here is submitted, and it's on arXiv. So in this theorem here, we actually have to be more specific about the domain that you start with, and I'm going to show you why. So if you start with the unit sphere in R3, the theorem says that there exists a conical perturbation, and it's illustrated here at the bottom. This is a conical perturbation. It's rotationally symmetric, such that the Neumann-Poincaré operator has infinitely many eigenvalues within its essential spectrum. It was relatively easy, in quotes, for us to prove that there are a finite number of embedded eigenvalues. But to show that there are infinitely many is really, that was the difficult thing, because these eigenvalues will converge to 0. And you have to get really careful bounds on all the operators involved when eigenvalues get really, really close to each other to show that they are genuinely embedded. So these are the two theorems. And I'm going to concentrate on the second one, because that's the newer one. But first of all, what is let me explicitly show you what the Neumann-Poincaré operator is, its definition. So here is, in 2D, a domain, but imagine this also being representing perhaps a 3D region. You have a normal, you know, the outside and the inside. The domain will be called omega, and the boundary will be called gamma. This is the green function for the Laplace equation in 2 dimensions and in 3 dimensions. And these are conventions for the signs. And our convention for writing down the Neumann-Poincaré operator, at least in this paper, is this one, the 2. And you see here, this derivative here is the derivative in the x variable. The x variable is the variable of evaluation, or I guess you could call it the influence point. And the y is the point of integration, the variable of integration, which you can call the source point. And this integral is taking place on the boundary. And we have a derivative in the fixed x variable. And you'll notice that this is actually, if the x were actually off of the boundary, not the x, I'm sorry. Yeah, so if the x, so if the x is off the boundary and then you take a limit going to the boundary, then this is actually the normal derivative of the single layer potential. Let me see. So this is the single layer potential here. And Kala, if I ever say anything wrong accidentally, let me know. So here's this derivative. And so you end up having this kind of a kernel. This D is either 2 or 3 in our case. If this is a smooth domain, then as soon as you have a corner, then or a conical singularity, then this becomes a singular integral operator. So the two operators that are going to be relevant in the analysis are the single layer potential, right here, just the green function itself, and this Neumann-Poincaré operator that I just defined. So the formal adjoint of the Neumann-Poincaré operator actually comes up in the analysis in a very nice way. And it's actually self-adjoint on a smaller space than L2. And that would be the derivative in the y variable. And that's actually the double layer potential. It's genuinely the double layer potential. So they're very closely related to each other. They're L2 adjoints of each other. So one of the things that happens in this business is that the K, the NP operator defined this way, and it's formal adjoint. When I say formal adjoint, I mean the L2 adjoint, where you just use the usual L2 inner product. This normal derivative in X turns into normal derivative in Y. But when we go to the energy space, just so you're keeping track of exactly what I mean by adjoints, it turns out that this thing itself in the new space in the new inner product will actually be self-adjoint. So it has a different adjoint. It's itself instead of its formal adjoint. So the adjoint depends on the space. So just to keep that in mind. Okay. So symmetrization is the step toward making the Neumann-Poincaré operator self-adjoint. And that's this theorem down here of Karl-Mikael Perfekt and Shapiro. Wait. This should say Karl-Mikael Perfekt and Shapiro. So I hadn't corrected that. So it still starts with a P. I know that Wei would often confuse Perfekt and Perfekt's names. Just so this should say Perfekt. So the symmetrization starts with the Plummelge identity, also known as the Calderon identity. This is the formal L2 adjoint. This is the single layer potential and boundary integral potential operator, and this is the NP operator. And so this is saying that the single layer think of this as being an L2 for now. The single layer potential actually conjugates the NP operator into its own adjoint. And because of that, just formal matrix or inner product analysis, linear algebra analysis, shows you that this Plummelge identity is really equivalent to saying that the K operator is actually self-adjoint or symmetric with respect to a new inner product given by this, what we call the S gamma pairing. So if you define a new inner product with respect to the single layer potential, that inner product is this. You can define it this way. Now the S gamma, you need this minus sign here to make it an inner product. This is an inner product in L2 of gamma in two dimensions. You have to be a little bit careful because there's a one-dimensional space on which it can be negative instead of positive. But you can take care of that quite easily. Now here's the energy space that I was talking about before, that mysterious energy space where the Neumann-Poincaré operator becomes self-adjoint. In this pairing, I said that it becomes, the Neumann-Poincaré operator, because of the Plummelge identity, becomes symmetric. So think about this still in L2, it becomes symmetric. But if you want to make it self-adjoint, I mean, it is a bounded operator. So if you want to make it self-adjoint, all you have to do is take the completion of L2 with respect to this new norm. And this norm here is actually a norm that's smaller than the L2 norm because of how this S acts. So particularly if you have a smooth domain, then this is a compact operator. So the energy space is the completion of L2 under this S norm induced by this inner product. And in electrostatics, you can actually interpret this energy space. So why is it called an energy space? It's actually equal to the charge densities on the boundary that have finite energy. Finite energy meaning in the bulk, in all of space. you can compute the energy. And if you look at all of those electromagnetic, those electrostatic fields that have finite energy, then where the energy is coming from the E field, then these are the charge densities associated with those fields. And this energy space is actually equal to h minus 1/2 of the boundary, but equipped with the S gamma inner product. And so this is actually very important. It's the same exact space, the same functions or distributions. When you take, so what I'm saying is that when you take L2 and you complete it with respect to this inner product given by the single layer potential, that space that you obtain is the same space of distributions as h minus 1/2. But you are using the S gamma inner product, which is equivalent, but to the Sobolev space inner product. However, you have to be very careful because as you change the gamma, and this is what we're doing in this analysis, we have to perturb the gamma in such a way to obtain this central spectrum, and you have to make that perturbation small enough so that we can obtain an embedded eigenvalue. So as you perturb that gamma, you're actually changing this inner product. You have to keep track of the particular inner product that you're dealing with. So even though for a fixed gamma, the h minus 1/2 inner product, or let's say norm, and the S norm might be equivalent, they need to be uniformly. I mean, how do you know that they're uniformly equivalent, right? And so we have to always keep track of the S gamma inner product and not allow ourselves to devolve into just thinking about it as this Sobolev space. So here's a theorem, and it says that when gamma is Lipschitz, then the Neumann-Poincaré operator is self-adjoint on this energy space. All right, so this is the first bullet here is just reminding you about some theorems about a theorem about the essential spectrum of, a theorem about the spectrum of a self-adjoint operator, which is going to be used. And so first of all, the spectrum, you can prove actually quite easily that when you see it in the right way, the spectrum of the Neumann-Poincaré operator actually lies between -1/2 and 1/2. Whether you have eigenvalues or continuous spectrum, no matter what the domain is, Lipschitz domain. And so here's just a standard result from the theory of self-adjoint operators. If you have an approximate eigenpair, which means that for the Neumann-Poincaré operator, meaning the k minus lambda applied to this is not equal to 0, but it's almost 0. In other words, it's less than some small epsilon times the norm, okay? Then the distance between that lambda and the spectrum is less than epsilon. It's just actually quite simple spectral theory of self-adjoint operators, which of course is not true for non-self-adjoint operators. So I want to back up now for a second and show you this result that I promised you for what happens on L2 if you take exactly the same operator, but you consider in L2, which is simply a smaller space, but it also has a different inner product, right? And on that space, this Neumann-Poincaré operator is not self-adjoint, it is not symmetric, right? Because its adjoint is a different operator because you have a different inner product. So in L2, it turns out that Maitreya, 2002, showed that each corner, this is Irina Maitreya, showed that each corner of a curvilinear polygon contributes this kind of a bow tie region to the spectrum. And inside each one of these different regions, it turns out that the Fredholm index has a different value. So this is actually essential spectrum. And so the sigma here, when you say it contributes a bow tie region to sigma, we actually mean the essential spectrum. So it's interesting, and it's a bit, you might say, more complicated. because it's not self-adjoint. All right, so here's the theorem. And I want to explain this in some detail because this is the main slide of the whole talk. This is the result that, oh no, it's not. Sorry, this is the results of Wei Li and me, 2019. And then this is the main result of the talk. Well, you can think of both of these as being the main result because I can't assume that I've done this talk for you before for the 2D case. So these are the two main results. And I want to talk about them in just a little bit of detail because after this, things will become very technical. And I'm going to do my best with those technicalities. So here's the theorem. This is the same domain I showed you before. The gamma naught here is a C2 curve. So think of the gamma naught as being the blue one, but you just can't see the full blue curve. So it would be, say, just a continuous or a smooth connection between this top part and the bottom part. That would be the gamma naught. It has reflectional symmetry about some line. And for each n in n, oh, here I actually wrote it correctly. For each n in n, there exists a corner perturbation. So this gamma now is the perturbed curve, and here's the perturbation. Such that the Neumann-Poincaré operator on the energy space for the perturbed domain has n eigenvalues within its essential spectrum. And we are now allowed to call it the continuous spectrum because Kalle proved that it is genuinely absolutely continuous. Not just continuous, but absolutely continuous. And so we can call these embedded eigenvalues in the strictest, maybe classical sense. So eigenvalues in absolutely continuous spectrum. And we proved this. Everyone in the business was absolutely sure, right, that the essential spectrum was absolutely continuous, and basically believed what Karl-Mikael had done in 1916, but kind of that it wasn't 100% proved, at least in the modern way of looking at things. And that's what Kalle did recently. So that's actually a very valuable piece of work there, which I still have to read in detail. So here's how it goes. What I'm showing you here is the Neumann-Poincaré operator, or its adjoint, either one. So this is on gamma. Gamma is already the perturbed surface. This corner here is actually imparting a certain interval of continuous spectrum from minus b to b. And this b is between minus a half and a half. You can explicitly find what that b is depending on the sharpness of this corner. As this corner becomes extremely sharp, the b goes all the way up to a half. And as the corner becomes, as it disappears, it becomes very shallow. The b actually goes down to 0, which makes sense because the essential spectrum should disappear when it's a smooth domain. And this here is the eigenvalue that we're proving actually exists within this continuous spectrum. So I want to give you just a little bit of intuition, especially for people who do scattering theory. You see this continuous spectrum here. What do the Weyl sequences or these generalized type eigenvalues look like? Well, Karl-Mikael knew this, and recently, or I guess a couple of years ago, Bonnetti and Zhang wrote a paper that tried to understand the continuous spectrum from the point of view of the Weyl sequences. So these generalized eigenvalues, or generalized eigenfunctions, or the actual elements that form the Weyl sequence, they are localized inside of this corner, and they become very large near the corner. But as you go away from the corner, they decay, or they could decay. But they're really due to the corner. And it's really interesting that if I had time to show you, you can do a a conformal change of variables that takes this corner and it blows it up into a waveguide, or like maybe a wave, maybe a wavy waveguide going out to infinity. And then this part here acts kind of like a scatterer of those waves. Anne-Sophie Bondia and some of her collaborators, Christophe Hazard, and I think maybe some others worked on that. And it's actually a very interesting application to scattering theory, or at least a connection to scattering theory. And so these here are really, you think of the states associated with the continuous spectrum as belonging to the corner, as really being localized in the corner. All right, so how do we get an embedded eigenvalue? Well, it turns out that these ideas that I told you about before, having a corner and having symmetry, allow us to do that. So think of the eigenstate corresponding to lambda as somehow being in the bulk, right? It doesn't care about the corner that much. That's kind of a heuristic idea. It doesn't care about the corner, but these things, the yellow ones, do care about the corner. So and there's some way separate, but the idea is that they might interact in the corner. And we have to get rid of that interaction that happens, maybe a weak interaction in the corner. And the way we do that is through the symmetry. And so here's the picture. Let's look at since this domain is symmetric it's reflectionally symmetric about L, you can decompose the operator and all of the states that it's acting on into the even and the odd components. The odd component, it turns out, has a central spectrum that is negative from -b up to 0. And you can do this through Fourier analysis localized at the corner by converting it into a strip. And you get things up in a way such that it also has an eigenvalue over here on the right that's positive. And so we're looking at for the odd component of this operator, the Neumann-Poincaré operator, we're trying to find a shape that has an eigenvalue that's positive so that it doesn't interact with the negative continuous spectrum. And then the rest of the continuous spectrum here is actually due to the even part. So it turns out that the even part of the operator has continuous spectrum that makes up the positive part of this whole yellow piece here. So this is odd, this is even. And then the idea is that this eigenvalue does not interact with the continuous spectrum because it is genuinely decoupled in terms of an orthogonal operator decomposition. And so this kind of makes it seem much less mysterious. And of course it is much less mysterious now because it's like two different operators, the even and the odd one, and they're not interacting. So this eigenvalue will not be disturbed, will not become a resonance due to any of this continuous spectrum because it's protected by the symmetry or decoupled by the symmetries. Now, the thing is that, so how do we find an eigenvalue here? We start off with the blue domain where we can find an eigenvalue lambda naught for the blue domain. And then, so here are the two ideas. And this might be the most important part of the talk. You start with the blue domain and you have a blue eigenvalue right here. Then you say, I need to do two things. I need to introduce continuous spectrum. And I also need, but in doing so, I will perturb this eigenvalue a little bit. And I have to make sure that it only gets perturbed a tiny bit so it doesn't run over and hit the central spectrum or disappear completely somehow. And so first of all, you have to choose this corner in such a way that you get the continuous spectrum, let's say the even continuous spectrum, to overlap this blue one. Then it'll end up being embedded, okay? But when you perturb with this tiny corner here, you do get continuous spectrum no matter how small this perturbation is. So you're allowed to make it as small as you want and still have continuous spectrum. And so now the second part of the analysis says, let's make this small enough and keeping the angle exactly the same, but just making it smaller and smaller so that this eigenvalue is perturbed a small amount so that it remains there for the perturbed operator as an eigenvalue. Now, how does this work in 3D? In 3D, we now have a conical singularity as our perturbation of the smooth curve, which is going to end up being a sphere. And we're going to prove there are infinitely many eigenvalues. What are the symmetries? Well, this is a continuous symmetry, a circle symmetry, right? Whereas the previous one was just a finite symmetry. It was just reflection about a line. So you have even and odd. So you decompose into even and odd only. In this case, you have this, because of the continuous circle symmetry, you now have Fourier analysis, which actually decomposes the operator into all of the infinitely many Fourier components. And the trick now is the following. We have to find a conical singularity here that has the right angle. So, well, the angle will now determine what the continuous spectrum is for all of the different Fourier components. This n here is the Fourier component. After you decompose the operator into those Fourier components, the 0th one means the 0th Fourier component. So let's say that the 0th Fourier component has a certain continuous spectrum, whatever it may be. We have drawn here negative and positive because there's no proof yet exactly what that continuous spectrum is, but one believes that it's actually positive. Now, so here, let's say this is the continuous spectrum for the 0th Fourier component. Now let's look at the arbitrary nth Fourier component. Let's look at its spectrum. Well, it's going to have a continuous spectrum that actually lives in a set that goes like 1 over n. So it actually decreases as the Fourier component becomes larger. And let's say that the blue curve, the blue eigenvalue is coming from the original unperturbed sphere. Now, Wei wrote 1 over n. It's not really 1 over n, but it's on the order of 1 over n. Okay, so let's say we have a domain where without the perturbation, we have an eigenvalue that's like 1 over n. So this would be getting smaller and smaller, right, with n. But for a fixed n, there's my eigenvalue. Then I want to make this perturbation in such a way that the eigenvalue gets perturbed a little bit, but it does not run into the continuous spectrum. Now that eigenvalue, the new eigenvalue for the nth component might not overlap this continuous spectrum of the 0th one, but as you go, if n is large enough, then this whole picture here becomes closer and closer to the origin. The trick here, the difficult part, or the part that really requires all the work, or a lot of the work, is that you need to find a single perturbation here so that this picture plays out for every single one of the Fourier components. In other words, a single perturbation will allow you to move this eigenvalue, perturb it just a small amount so that it does not run into the continuous spectrum. And small enough so that all of these red eigenvalues for the different n's will actually converge to 0. In fact, we find a subsequence that will converge to 0. And actually, because they converge to 0, as n becomes large, they will, for large enough n, they will actually overlap this continuous spectrum of the 0th component. And that's how it works. So the analysis involves carrying out all of these heuristic arguments that I just gave you. Okay. So this is kind of, what's going in our...
May I ask a question? So could you remind us what the properties of this green bit are? So do you know any quantitative?
Right here?
Yes.
So this again, this is the essential spectrum for the 0th component. So the Weyl sequences, or the generalized eigenfunctions associated to this, would look like they would be concentrated in the singularity, and they would also be rotationally invariant. Yeah, is that enough for now?
But how big can the green bit be?
Oh, so there's Kalle has let's see. I think this was okay. I should have actually shown you the reference, but there are bounds on exactly what the endpoints of these things are. They as n goes to infinity, they actually converge to zero. And I don't know what the actual number is. It's something that you can compute. There's a complicated expression involving Legendre functions. Okay. And Kalle, maybe you could say something more specific right now. Probably without writing more stuff, I can't say more, but they do just converge to zero. But one knows bounds on what the essential spectrum is from Kalle's work on conical singularities for the NP operator.
Okay, thanks.
You can write it down, yes. Mm-hmm. I think I took that stuff out because I wanted to make this wanted to leave some of the details out. So let's see. So here, now I'm going to go through some of the elements of the proof. So as I said, let me see how much time I have actually. 51, so I have about 9 minutes, right? Okay. So what I'm hoping is that what I've told you so far shows you the heuristics and really helps you understand, why this ends up working and what the difficulties are and what the analysis has to try to crack. Okay, now I'm just going to show you a few elements of the analysis for the 3D case. It turned out to be very complicated. It's a technical looking paper, and I'll try to show you, a few things. So first, the first thing I said is that by rotational symmetry, the Neumann-Poincaré operator decomposes into Fourier components, and we call these K and gamma. So gamma is going to refer to the whatever curve you're on. So for this for rotationally symmetric curve, you can say that it is generated by a curve in the plane. So let me see. Do I have, okay. So here's the rotationally symmetric surface. So think of a curve starting down here and being a parametrized curve starting here and going all the way up to the top. And then you would rotate that curve around. And that's how you generate the curve of the surface. And that curve here will be called little gamma, lowercase gamma here. So gamma 1, gamma 2 are the two coordinates, the horizontal and the vertical coordinates of what I was just, of what I was just showing you right here, gamma 1, gamma 2 coordinates. And so once you rotate it around, you see you have the rotation here. The gamma 1 coordinate becomes the two horizontal coordinates, and the gamma 2 is still the vertical component. And then you can, so let's say that the gamma 1, gamma 2 are Lipschitz, but for our purposes, it'll be smooth, except it will be set up so that you have a conical singularity at the bottom. Then you can do the Fourier analysis. You can look at the Fourier components of the functions in the function space. You can also decompose the kernel into Fourier components. And then you can decompose the two operators, the Neumann-Poincaré operator and the single layer operator, into Fourier components. And of course, the L2 and the energy spaces all come into play here. Now, here's a very technical part of the whole thing. In order to get those delicate bounds that I was telling you needed to get, remember you need the uniformity in the n and the amount that eigenvalue was perturbed. Well, it's a relative uniformity, right? Because as the n becomes larger, you have less and less room for that perturbation to take place in, right? So you have to have careful bounds on those perturbations and on the operators. And in order to do that, we use this representation, which I think first was written down in a paper of, Kalle, tell me if I'm wrong. This was you and Helsing, right? Where you write down the Fourier components. This was in your paper on the conical singularities. The Fourier components can be written in this way, where I'm going to show you what the Q is. The Q is a half integer degree Legendre function of the second kind. This is the definition of the Q as a function of its argument, here called called chi, integral representations for these Legendre functions. And then the R is some combination of these. It took me a long time to get my brain even to try to understand and work with these things, and I still have trouble with them. But you know, it's just step by step trying to understand how these things work. I don't know. I think that they're hard. So you can write the kernel in this way using the Q and the R. And then so this is the kernel for the Neumann-Poincaré operator. Here's the kernel for the single layer potential. That's it's simpler. It just involves the Q. And the argument chi is actually this thing. So remember the gamma was the vector curve. It was this thing itself. Okay. So that's what the kernel actually is. So 1 minute's not going to give anybody enough time to actually think about this, but just to show you, we have these representations, and we have to actually use these and use properties of these Legendre functions to get appropriate estimates. Here's another important part of the analysis. So you might be wondering, why do we just use a sphere? Why could we not extend this to other kinds of domains? Well, we cannot at this point. And it turns out that in the analysis where, remember I showed you that you have, as you do the perturbations, you have to keep track of the inner product that you're dealing with, which is the S inner product coming from the single layer potential. And that has to be then related to the Neumann-Poincaré operator, because you're trying to get bounds on the Neumann-Poincaré operator with respect to the S norm. Okay, so there have to be some relations between S and K. Now for the sphere, S is 2 times K. Of course, they're acting in different spaces, but the kernels, they satisfy this. And it turns out that we need this precisely in the analysis that where I just described, right? The relation between those two. Now, so you can write down all the eigenvalues for the Neumann-Poincaré operator for the sphere explicitly. That's another very nice thing. You can write them down explicitly, and that's just because we know so much about the sphere and we have the spherical harmonics, and we can write the eigenvalues and eigenfunctions in terms of spherical harmonics. It's something that is really unique to the sphere, and then allows us to do a lot of the analysis. So some of this boils down to hard analysis. Now we have to perturb the sphere by conical singularity, and that imparts the interval of essential spectrum, as I described before, of size 1 over n. And how much? Yeah, I'm not sure how much of this I should talk about. Let me see. Anyway, here's a lemma. And the lemma is okay. Forget the first one. Look at this right here. The lemma is telling you something about the essential spectrum. Okay, for the Fourier components, and this is the kind of estimate that we need. But the essential spectrum that I was showing you, those intervals, that they are bounded by what? It's like 1 over n. So you see the 1 over n here, and this always happens, and that's good. It goes like 1 over n, but we need a lot more control than that. It's it's controlled by the distance between, alpha was the angle of the perturbation of the cone, and pi over 2 meant it was exactly flat, because it was the half the exterior angle. And so alpha minus pi over 2 is measuring how flat the angle actually is, how flat that conical singularity is. And so in order to get control over the essential spectrum, making it small enough so that the eigenvalue stays outside, you have to make the perturbation flat enough. That's one of the elements in the theorem. Now, one of the techniques there is that the Mellin transform almost diagonalizes the operator near the conical singularity. In other words, if you just have a cone itself, then you can use the Mellin transform to diagonalize the operator. In other words, it gives you a spectral resolution where it becomes a multiplication operator. It's harmonic analysis for the cone. But now you just have, locally it looks like a cone. So you have to try to manipulate the Mellin transform to get the results that you want, that you know work for the cone. It's much more complicated than meets the eye, even though a lot of the intuition seems that it should work, but it ends up working. So here's the theorem. I mean, one of the very many lemmas. If the perturbation is sufficiently small and shallow, in other words, the angle is not very large, and with controlled curvature. So you somehow have to set things up so the curvature is not too large, because the curvature starts to make the integral operator more and more singular. So in other words, if you have a large curvature in the boundary, as that, if that now then becomes an actual point, then suddenly the operator becomes very singular. So you can imagine that as the curvature becomes larger, that you have more and more problems, less control over that operator. So you need a certain control over the curvature. And then once you have that, what you're going for is the distance between essential spectrum and the nth eigenvalue. Say lambda n will be one of the eigenvalues, let's say the largest eigenvalue for the nth for a component for the sphere. And then you can get a control over that distance in terms of two things. So look here, this is how shallow, remember the alpha over pi over 2, that's how shallow the perturbation is, and the epsilon is how small the perturbation is. So those are the two different elements that you need to manipulate. And it turns out, just to tell you what ends up being an issue, is that if you make the epsilon too small compared to this, then the curvature gets too large, because you're trying to fit a certain angle into the sphere. But when you make it very small, the curvature gets so the angle and the smallness have to be correlated with each other in order to make the whole argument work. So this is now stuff that you don't really want to see. So I'm just going to tell you what's going on. So just to show you, yeah, there's a lot of technical stuff here. Parameterize the sphere in a very specific way, so that when you do the perturbation, you see, we have all of it turned out that we have all these 6 different properties of the perturbation that allows you to control the curvature, allows you to control the derivative, allows you to get all the bounds that you want. And so all these technical conditions here are basically saying that in this picture, you have some epsilon and you have a given alpha, and you have to correlate them. So the curvature, you see the curvature of this connection. You start with a little a cone here, a genuine piece of a cone. And then you have the sphere up here, and you have to connect that cone to the sphere. And as you do it, you have to kind of connect them like this. And it seems like, oh, that should not be a big problem. But it turns out that's really something we have to pay a lot of attention to in the bounds, because those estimates become very technical when you imagine the representation of the Fourier components of the NP operator that we're using those special functions. And so we really have to do this with quite a bit of care. And so look, right here, this lemma is just showing you that finally, if you look at the NP operator on the original unperturbed curve or surface, compared to the perturbed one, of course, they're different domains, so you have to actually relate them through the parameterization. That's why you can really take the difference. That's really what this means. Even though they're acting on different spaces, it's through the parameterization, through a common t variable, that you can actually do this comparison. The NP operator, as you perturb it, is controlled. The perturbation is controlled by, as I said, how flat the angle is and how small the perturbation is. Whereas the S operator, the single layer, is controlled just by how small it is. It doesn't care about that angle because it's a much less singular operator, right? It's a smooth one. And then we end up getting what we want with the spectral distance theorem. And I know you don't want to see this proof, and don't look at it. All I want to show you is that you're trying to find an approximate eigenvalue of the perturbed operator, you see? And then all this stuff here, all I'm trying to show you is that you have to use, remember I said before, you have to use the S inner product. And so you have to stick, you have the S norm here. So when you put the S in there, you have to somehow relate S and K. Okay, and that's why you need, it has to be a sphere at this point, because we have a relation between S and K. And that allows us in the end of here to have the result pop out that we want. So anyway, things like this are involved in the proof. And then we come back to the picture that I showed you at the beginning, now with maybe a bit more understanding that this is the nth component. We had to perturb the eigenvalue just a little bit. That's making the epsilon small enough. And this had to be controlled for all n's simultaneously. So this picture here becomes infinitesimally small, where we have to know that this red eigenvalue, perturbed from the blue one, does not hit the essential spectrum. And that you have to find infinitely many of those will then overlap the zeroth component of the continuous spectrum. Yeah, so the positivity of the central spectra for all the different n's is not known, although numerically it's like all but sure. For the zeroth component, it does have a positive part. So that's why we can use the zeroth component to embed all of these eigenvalues. So that's one of the questions that remains open. And yeah, so one of the questions we really would like to understand is, what about other surfaces other than spheres? I mean, why is it something so, we needed to know something very specific about spheres, which is the relation between the K and the S, but it's not something that you have in your hand for general, domains. And so that relation to try to connect the K, bounds on the K in the S norm is the difficulty. Yes, and can you get infinite number of embedded eigens for each one of the Fourier components? Is another thing. Right, so I believe I would like to stop right here, because the rest of this is just an appendix on some of the proofs. All right. So thank you for listening. I really hope that this technical stuff, at least that you would be able to see what the, what the heuristics are, and maybe a few of the technical details.
Thank you very much. Thank you very much for the talk, I'm sure. We have a lot of experts in spectral theory in the audience. So, questions?
Do you hear me, guys?
Oh yeah, I hear you.
Yeah. Hi, Stephen. Sorry, I had to ask this question because this morning I had to give a lecture, and for some reason my mic was there, the laptop mic. So I'm just using this camera to, because it has a mic in it. So the question is the following: you at the start of the talk you said about this generic scheme that is normally used nowadays to construct these embedded eigenvalues. So you use certain symmetries to split the operator into components and then construct embedded eigenvalues which are in the gaps for some components, right?
Yeah.
Is there any other methods in this topic that people use?
Yes, so I've been working on, I got interested in embedded eigenvalues through multi-layer graphene. And so this is quite a different type of operator, but I'm thinking about differential operators on graphs, so quantum type graphs.
Actually, your paper on graphs, on periodic graphs, is open just in front of me.
So they're actually one of my main motivations. This is the 2019 and the 2021. In those papers, I was explicitly interested in how can you get embedded eigenvalues when you don't have the symmetry to help you.
Oh, maybe it's the wrong one. I've got 2014, so it's...
no, that one, that's the easy one. That's where I use symmetries.
That one uses symmetries,
Yeah, and that one, I got motivated for that one because, well, the theorem of Kuchman and Weinberg that basically says that you can't have embedded eigenvalues. And it's because the reducibility of this dispersion function, the Fermi surface, right? And so that's the answer to your question. The way that you can construct these things, and the two papers that you're seeing now, the 2019-2020, don't actually have the construction of the embedded eigenvalues, but we can do it on a chalkboard, and we'll do that. So what you do is so the main idea here is that, let me see okay. You have to somehow reduce the operator into two pieces. Now, an orthogonal decomposition by symmetries will do that, and it'll make things really easy because it's really like one operator here, one operator there. They don't care about each other. Yeah. But now the reducibility of the Fermi surface, which is really factoring the dispersion function between energy and momentum. That's a little bit subtle, but being able to factor that actually turns out to be much richer than an actual operator decomposition into two different graph operators. That's what those papers deal with. So you, even if you don't have the symmetry of the graph, like you could have, say, graphene, another layer of graphene, and then you have potentials between the, say, not symmetric. So you do not have like any reflectional symmetry. But if you set up the potentials in the right way, even if they're asymmetric, there's certain conditions on those potentials that the 2019 paper shows, then you still get reducibility of the Fermi surface, but not of the Bloch variety, which, so it's a richer thing, and then you can still get embedded eigenvalues in that way. And so the answer would be yes, even without symmetries, there's some other kind of algebraic reducibility. It's richer than the pure operator reducibility coming from symmetries. That's the short answer. Yeah.
So I need to read those papers on you. Okay. Let's understand what's happening. Yeah. Thank you very much.
You're welcome.
We have a question.
Oh, by the way, Mikhail, the 2019 paper, there's something called an asymmetry function that we used. We actually understand that much better now on with Malcolm and Ian Wood and Carl Schmidt, in case you're wondering about it when you look at it.
Great. Yeah, thanks.
So I have a question. This is Massimo Lanteri-Christoforis who raised this.
Okay, yes, I have a question. In your pictures, the cusp is pointing outward, which corresponds, roughly speaking, to gamma 2 prime 0 greater than 0.
Yeah.
And I'm asking what happens if the cusp is pointing inward, which means
what happens? Yes. So what happens when it's pointing inward is that the even and odd are switched.
Okay, so it's not really a new.
Okay. That's right. And then so you could do it either way, right? So if you had if you wanted the other way around, like the mirror image, I think, of this, you would have to use the inward pointing. Yeah.
Oh, I see. So another question related to this point is that if you take it inside, let's say the cusp, then although you lose Lipschitz continuity of the set, although you still preserve the cone property because you still have the cone inside.
Yeah.
So you're saying that actually there is no improvement if the cusp is inside or outside.
No, there's no improvement. No.
The presence of the cone.
That is correct.
Okay.
That's correct. And if you look at Kale's paper on this, so actually either one of these, if it's going inside, Kale, can you remind me? I think that the spectrum goes to the other side, right? Or it's kind of reversed.
So it's reflected. It's reflected in 0. So I mean, so the problem is that we don't know that this green interval and also the corresponding intervals for the higher modes, like it looks like they're positive, and it seems like there should be some fundamental, not so difficult reason for that, but I don't know what that reason is. So, but if you knew that, then it would be completely clear what happens if you make the the conical point inward pointing, you would just get the same construction, but with eigenvalues accumulating to 0 from outside the spectrum. But because, I mean, we have this, yeah, like because we don't know that they're positive, it's something it's this point that I find kind of embarrassing, because it seems like someone could just, at any moment come and say, this is why they're positive. But so, yes, I wrote in the chat that this would mean that that the operator, it's on the infinite cone, that is a positive operator. And it's not just a consequence of convexity, but there has to be some kind of geometric reason that that's true, that I don't know what it is. So if someone does know, then please do let us know. We'd be very interested to know why these intervals are positive.
In any case, it is true that it gets reflected. Exactly. I mean,
yeah, that's true. Yeah. But yeah, so then that's true. Sorry.
Yeah.
Thank you.
Further questions?
I have a question coming back to this reducibility, this algebraic property.
Yeah.
Is this also a way to see, for example, a difference between, say, the Fermi surface of the Laplacian and the bi-Laplacian when you do this? I mean, over the reals, it's the same, but if you factor over the complex, then it's different, right? You would get complex solutions for the bi-Laplacian, but not for the Laplacian, for example. Does this play a role, this kind of?
Let me think about this. And you're talking about for homogeneous.
Let's just say in 1D, I take the Fermi surface corresponding to xc squared minus 1.
Yeah. I see.
Just plus minus 1. But if I take c to the 4 minus 1, I have plus and minus I in addition.
Yes. But yeah, I know what you're talking about. Okay, so and I believe the answer is the following. Although I don't think I've thought about it carefully enough to say it's definitive, but I think the answer is the following. It's known for like fourth order operators, such as that one, by Laplacian, that you can get embedded eigenvalues in the continuum. And it's exactly that. I mean, that's exactly how you do it. Well, you go to the Fourier domain, and then you have the operator written as the product of, basically the product of these two polynomials equals some forcing. And then you try to solve. Now, so having embedded eigenvalue is very similar to just having a forcing within the continuum that doesn't radiate.
Mm-hmm.
Very much related to that. So suppose I have a forcing here, and the Fourier transform of the forcing actually cancels the component that has the c squared minus 1, the one that does that you do see, where you do see in the real domain in the spectrum. Well, now you have a solution that you can actually solve for this, an L2 solution. But it's because you still have the c squared plus 1 there, right? So you can actually solve because you have another component that does not hit the Fermi, that does not hit the torus. I mean, it doesn't hit I'm sorry, in this case, the real line, the real, where you see the spectrum, right? So you're absolutely right about, that's exactly the mechanism that you pointed out. You have a component of the Fermi surface that does not intersect the real, it's not part of the real Fermi surface, right? It's complex. And so it doesn't show up as singularities when you solve in the Fourier domain.
Mm-hmm.
And it doesn't show up as singularities in the real part where you take the inverse Fourier transform, right? Mm-hmm. It's just over the reals, but it's in the complex. And so there's kind of like this surface of poles that would then contribute.
This basically has to do with, for the eigenfunction, this means that the eigenfunction would be genuinely in L2 and not just
exactly. It's genuinely in L2, and it has infinite support. It has a certain decay. That's right. These are the kinds of things that I've been interested in for second order operators, which cannot happen in the continuous case, at least that's the wisdom, unless someone can find a situation where you can reduce the Fermi surface in 2D. But that's, you know, you're not supposed to have that happening. But for quantum, for graphs, you have these additional symmetries, but not just symmetries, but also ways to reduce the Fermi surface that did not happen, that cannot happen in the PDE case, say periodic Schrodinger operators, right?
Yeah, I understand. Thank you.
Wisdom is it doesn't happen, although I don't know if it's all of that's completely proved. But yeah.
Okay. Thank you.
That's right. It's exactly the mechanism.
Are there further questions? I have one. So in your slide 8, you have this B.
Yeah.
You showed us some bounds in terms of the angle in the 3D case. Do you have any quantitative relations between these B angles?
Yeah, people know exactly what this is. This has been known along since the beginning, and you can write down the B. Let me see exactly what it's very simple. It's just the absolute value of pi over 2 minus the angle with the appropriate constant in front. It's linear. It's linearly controlled by the angle.
Okay.
Yeah, that's right.
Okay, so
and that comes out of what Kalle was saying, where you go directly. What Kalle did with Shapiro. With Poutinar. If you do the analysis on an actual infinite wedge, and then you go to the Mellin transform, diagonalize it, and it comes out of that calculation. Continuous spectrum. You just look at it comes out of the functional calculus through the Mellin transform for an infinite wedge.
I see. So it's very much the same behavior in 2D and 3D.
In that regard, yes.
Thanks.
Yes, that's right. Yeah, in 3D, you still use the Mellin transform. You use a wedge, but you reduce each one of the Fourier components to a 2D thing. Yeah. And then it has a different kernel, and you look at the kernel. Take a look at the paper of Perfekt and Poutinar on that. They did 2 of them. And the second one, they do a very nice analysis of the infinite wedge. I forgot exactly what's where.
Okay, any more questions?
Maybe just a lame question. So Fermi surfaces basically are these surfaces that create bands of periodic operators, right? Is it this the right way? Because this is just a different language. I'm not familiar with this.
Yeah, right. It is. We have the Bloch, the quasi-momentum.
Yeah.
The energy, and then you just take the dispersion. Dispersion function, which is the function whose zero sets, right, are the Bloch variety or the dispersion relation, and then the Fermi surface is you take a fixed energy and you look at the level set for the fixed energy as a function, and so it's a variety in the quasi momentum for a fixed energy.
Oh, I see. For fixed energy. Yeah.
You see, that's actually why it's much harder so the Bloch variety is the variety in energy and momentum. Now, if you fix an energy, now you have a variety in momentum space.
Yeah.
And the factorability, say for quantum graphs, has to be in terms of polynomials or whatever or analytic functions.
So
analytic factorability.
If you take a 2D situation, the Fermi surface would be just a curve.
Yeah, it would be a curve.
Okay, so I interpret it correctly.
That's right.
Yeah, okay.
That's correct.
Yeah.
Right.
Thanks.
There's a nice book on Fermi curves for discrete operators by Knörer, Giesecke, and Trubowitz. It's a 1990s book on just curves, which is kind of nice.
Right, thank you.
You're welcome.
So if there are no further questions, let's thank the speaker again for the very nice talk.